Hello, Assalamu alaikum. In this lecture, we will talk about some applications of linear algebra, uh, and one of the first application that we're going to discuss is with respect to difference equations. And difference equations are a very common phenomena in electrical engineering. They normally appear in communication systems, in signal processing, in control systems, and whenever you sample an analog signal, this kind of difference equations do occur. Yeah. And now, for example, if you are sampling an audio signal, uh, so so it means all these samples that you are generating um, can be can actually form a set of difference equation. Now, for example, uh, we can now formally define it. We can say a signal in S is a function defined only on the integers, and you can think of, and you can visualize it as a sequence of numbers. So what you do is you have a signal, an analog signal or a continuous signal, for example audio signal, so they may be changing up and down here. So what you do is you sample the signal at a discrete set of time, say let's say 0, 1, 2, then you have it 3, sample it 4. So it means the signal values only exist at these discrete times, which is 0, 1, 2, and 3, 4. Previously it used to exist at for every possible value of t, but now it is existing only for the integer values of t, which we say is x of k, or say y of k, and y of k only exists for k 0, 1, or even 2, 3. Even I actually can refer it as k is equals to minus 1, so for depending on type of signal and depending on where your zero reference is. Okay. Now, one of the few examples are the signal which is let's say you can say y of k is 0.7 to the power k, then you have y of k as 1 over k, then you can similarly have y of k as minus 1 over k. So 0.17k will be nothing but a signal that will be decreasing with the increasing values of k, which is 0, 1, 2, 3, 4. 1 of k for all values will remain the same as 1. Similarly, minus 1 to the power k is a signal that will be alternating in sign depending on the values of k, right? So it says 0, 1, 2, 3, 4, 1, 2, 3, 4. Similarly, you can have on the negative side as well, which is here, which is here again, and similarly so on and so forth. This will remain constant for all minus 1, minus 2, and so on and so forth. So as I told you earlier, one of the very prominent example of these discrete signals that lead to actually difference equation is an audio signal. So audio signal is one prime example. So what you do is basically you sample the signal, and you sample the signal at discrete times, and you record the values of the signal at discrete times. In addition, what you get is a discrete time signal, and this is a kind of discrete time signal that is present, that your mobile phone operates on. So mobile phone has a microphone that in which you speak, and this is the signal caught by the microphone, and a digitizer actually convert this analog signal into a digital signal in a discrete time signal, and perform some processing for transmission. Now now this signal that you can get from different sources, these discrete time signals, not specifically audio signals, um, can have uh, a form like which is um, for all k. So you can now think of this signal forming a space S of signals, as I discussed earlier. For example, 0.7 to the power k, 1 to the power k, minus 1 to the power k are actually three signals. Okay? And say if similarly we have three other signals which are defined by, let's say, u of k, v of k, and w of k, and assume if I assume that u of k, v of k, and w of k are independent signals, right? It means c1, c2, and c3 must be equal to 0. Now because there's an index k, so it means this condition is true for all the possible values of k, right? Now it may not be true for certain value. If it's not true for a certain value of k, it means that these set of vectors, these set of signals, u of k, v of k, and w of k, are not linearly independent, and in this space of signals, and may not be classified or you can say classified as forming the space, signal space. Okay? Now let's say, for example, if for three values, suppose we say c1, c2, and c3 satisfy this equation, the above equation, okay, and it holds for then and the equation 1, equation this one, which is a 1 here, holds for any three consecutive values of k. Let's say k plus 1, and k, which is k plus 1, and k plus 2. So for those three values, we can actually write this as c1 u of k plus 1 plus c2 v of k plus 1 plus c3 w of k plus 1 equal to 0. Similarly, we can write this as c1 u of k plus 2 plus c2 times v of k plus 2 plus c3 times w of k plus 2 equals to 0. Now, so it means I can write this equation as u k, u of k plus 1, u of k plus 2, and this as v of k, v of k plus 1, v of k plus 2, and then you have w of k plus 1, and w of k plus 2, which should be, so it means is c1, c2, and c3 equals to should get 0, 0, 0. Now this matrix is called causality matrix. this matrix is called Casorati matrix, and the determinant of this matrix is called Casoratian. Okay, so determinant of this matrix, determinant of this matrix is called Casoratian. Okay, right. Now, so if these vectors are, if these are linearly independent, which is, this is true, so it means this matrix is actually invertible, right? So we can actually show that that for that your for example, if I say u of k is 1 of k, and v of k is equals to minus 2 to the power k, and w of k is 3 to the power k, are linearly independent signals, right? So the thing here is I can write this as 1 of k plus 1, 1 of k plus 2, using the Casorati matrix minus 2 k plus 1 minus 2 to the power k plus 2, and I can write 3 of k plus 1, and 3 of k plus 2, right? Now what I can simply do is to that this to show that this matrix is invertible, right? So if it is invertible, it means these signals are actually linearly independent, right? So for that, to prove that, we can simply take any value of k, which, let's say in this case k is equals to 0. So what I'll get here is 1 1 1 minus 2 3 1 4 9, and if I do this row operations, I can have the form which gives me 1 0 0 1 minus 3 0 and 1 2 and 10. So we can see here, this is also in, there are 3 pivot columns here, and this is a 3 by 3 matrix, so it means the column space is same as n, so it means this vector is invertible, and these signals are actually linearly independent, right? Now once you get these signals, right, in the signal space, we can have we can manipulate those signals, and how we manipulate those signals is by simple addition, multiplication of the observed values, right? So for example, I sample the signal, and what I want to do is to obtain a certain kind of sequence from these values, which is, so y k plus n. So I take n values of that signal that I just sampled, and what I want to do is to obtain a kind of a desired sequence z of k. So this is kind of a sample. You can think of this as a sample signal. Y is a sample signal, and what you want to do is to make use of its previous values to obtain z of k. So this kind of equation, you will see that is called as linear difference equation. Or generally you can say this linear recurrence relation of order n. Generally we take for a naught, we take it equals to 1, and now, so as we have seen earlier, if we say zk is equal to 0, it means this becomes a homogeneous linear difference equation. It becomes homogeneous. If zk not equals to 0, that becomes non-homogeneous, right? So for example, difference equation, such this kind of difference equation is normally used in filtering, and this filtering, the choice of a naught, a1, and these coefficients actually determine what kind of filter we're going to have for the signal. Right? It can be a low pass filter, it can be high pass filter, depending on the values of a naught, a1, and an. Right? So now, in the first case, because this system can have two possible set of scenarios, in which one is set of k is equal to 0 and the second one is at k not equal to 0. So let's look at the first scenario, in which we have such that yk plus 3 minus 2 times y of k plus 2. There are some coefficients values of a0 and a1, and a0 is always 1. So minus 5 of yk plus 1 plus 6 times y of k equals to 0. So what we need to find is the solution of y of k, what kind of sequence what kind of values of y will help us obtain the 0 for the sequence. Now actually, in order to do that, as you are seeing in ODE, that for these kind of equations, sometimes you have to assume a solution and you have to plug in that solution to find the values, to find that if a certain solution exists or doesn't exist. So it means a general solution of this linear differential equation has the form y of k is to r of k, and if I plug in y of k, r of k in that equation, I'll get here is r of k, which is here r of k plus 3 minus 2 r of k plus 2 and minus 5 of r of k plus 1 plus 6 times r of k equals 0. And so if I do simple bit of calculations here, which is r cube minus 2r square minus 5r plus 6, so I can factorize it in the form which give me some possible solution. So r minus 1, r plus 2, and r minus 3. So you can see here that there are many possible values for r. R can be 1, r can be 2, and r can be 3, because then the solution is the form r of k. So it means 1 to the power k, 2 to the power k, 3 to the power k are actually are actual possible solutions for this homogeneous difference equation, right? So generally, when you plug in the value, this kind of assuming that this linear differential equation has this kind of solution, the resulting equation, for example, this equation is called auxiliary equation, right? Auxiliary equation. Okay. Now so we have in this case here, we have from that auxiliary equation 1k, 2k, and 3k as possible set of solutions. We are not in this example or in this course, we are not going to talk about the when r has a repeated root of the auxiliary equation, because this is the topic that you're going to cover in digital signal processing, or when you are studying filter design, right? Similarly, what we can say here, generally, so what we can write for solution set for linear differential equation is that if you have a1 to an, then you can consider the mapping T to S that transform a signal y of k into a signal z of k, w of k, and we can say that w of k is equals to y of k plus n, so on and so forth, to a n times y of k. In the previous example, we were taking w of k as 0, right? Now the set so in this case the set of signal that map t that maps into the zero signal. Okay, so we know that this is actually the subspace of S of the signal space, and any linear combination of that of solution is again a solution, as we have discussed previously, if you remember, when we are talking about solution set of system of linear equations of homogeneous and non-homogeneous equations, that this kind of situation does happen, where you have any linear combination of that solution, actually, or the set of solutions actually becomes a solution. So what we are saying, that because that linear combinations of that of solution, for example, in this case was, in the previous case, 1 to the k, 2 to the k, and 3 to the k, actually can all become form the subspace for the solutions for subspace for the solution of the homogeneous difference equation that we solved previously. So we can say that from that thing here, the set H of all solutions of the nth order homogeneous linear difference equation is an n-dimensional subspace. Okay, now so similarly we can see here, so if I say this as y of take example of y of k plus 3 minus 2 times y of k plus 2 and minus 5 y of k plus 1 plus 6 times y of k equals 0 for all k. So we know that from that equation, the linear difference equation that we solved earlier, that 1 of k, 2 of k, or 3 of k, or minus the power k are actually the solutions of this this homogeneous linear difference equation. So 1k minus 2 to the power k and 3 to the power k are actually linearly independent solutions, and any linear combinations of that actually of these three independent signals forms a basis for the solution space. So look here. So if you look at here, so it means sorry, it's minus 2 to the power k. So all these actually forms the basis for the solution space of this homogeneous linear difference equation. Similarly, we can look at the non-homogeneous part as well, in which we intend to have this kind of thing where y k of n plus a1 y of k plus n minus 1 up to a n y of k equals to z of k, and it is for all k that equation is as well. Now this is very much similar to the scenario we were talking about. Ax is equals to b, so we have the set of values in A, give matrix A, and we want to achieve a transformation that translate this point x to b. So we can um, we can use that very fact that we have learned in our previous lectures to solve this non-homogeneous linear differential equation. Although there is no kind of standard solution for non-homogeneous linear differential equation, but but let's do an example to in which we were given already we already given a solution. Verify that, for example, in the signal that y of k is equals to k squared satisfies the difference equation y of k plus 2 minus 4 y of k plus 1 plus 3 times y of k is equals to minus 4k for all k. So this is a non-homogeneous linear difference equation, and what we have to prove that y of k square is a solution for that for equation, right? So in that case we can substitute this as k plus 2 whole square minus 4 into k plus 1 square plus 3k square, and if I solve them up, what I get here is minus 4k, right? So it means the right hand side is equals to left hand side. Now k square is actually indeed a solution for this non-homogeneous linear difference equation. Now if I find an auxiliary equation for this equation, we know that I put this one equals to 0, and from instead of y I assume that y of k is nothing but r of k. So in this case I can say that the auxiliary equation that I get from this for its homogeneous part is r k r squared minus 4r plus 3 equals to r minus 1 into r minus 3 equals to 0, right? So here we have r is equals to 1 and r is equals to 3 as a solution of this auxiliary equation. And now if you remember from our early discussion and again the solution when we're talking about the solution of system of non-homogeneous equations, that there are two parts of the solution of this non-homogeneous equation. One part is from the homogeneous part, and then one is from the non-homogeneous part. So in this case and thing here is if you remember, if it was a solution is a line in the case of non-homogeneous, effectively there was a line parallel. It just the solution actually of a non-homogeneous equation actually shifts parallel to that line. So similarly in this case we have from the homogeneous part 1k and 3k, r is equals to 1 and r is equals to 3, which is solution is r to the power k. So 1k and 3k are the solutions for the homogeneous part, and k square is the solution for the non-homogeneous part. So it's quite very similar to the one that we discussed earlier, and you can think of this as and now the solution as x1, x2 and x3. x1 in this case could be 1 to the power, so you can think of this as the lower part as spans of the vectors. It's a span of 1k and 3k, and just remember to this one we have a span again shifted by k square, which is here, and k square plus span of 1k and 3k. So similar to that very scenario, for ax equals to 0 and ax equals to b, this has a very similar interpretation in terms of those solutions. Okay, I hope you have understood this concept. In the next lecture we'll talk about application of linear algebra to Markov chains. Thank you. Allah Hafiz.